this vector called the visited vector or unvisited vector. And every time you visit a vertex, you put a check mark or a 1 in it, which means don't go back there again. Because if you do, you can cycle. Okay, so therefore we're going to start with A, because that's the choice we made, arbitrary. And then we're going to go, definitely, the only place we can go is to B. And from B, we're going to go immediately to C, because we're going depth, not D, not C, because we're going to keep them in key order. So we're going to go from B to C. And from C, the only place we can go to A. But we can't go to A because we've been there before. We kept track of that. So that means we were going to recurse back to B and go to D. And from D, I have two choices, A and C. I've been to A, I've been to C. So what am I going to do? I'm done. I'm going to go back recursively. I've been to C, I've been to D. Any others?
No.
I've been to B. Any others?
No.
I'm done. So the sequence of order is exactly what we did, A, B, D, C. How about if we started at E? What's our depth first? So we start at E. We're going to go to F, to B, to C, and to A. Can't do this. D. Where do we go? Ding, 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 ding. Good one. Now from here. Okay, we're good here? That's it. So, by the way, that means we've been there before. That's the international sound for no. Ding, 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 ding. It's the international sound for go there. All right. So that's the idea, and this is the algorithm is outlined here. I'm not going to bother with this too much, but this is the idea. Visit vertex V. So DFSA, A comes into here. Visit the vertex. The vertex you're given, you visit it immediately for depth first. Then for all the neighbors W adjacent to V, we're going to loop for all our neighbors. So if we start at E, our loop for W will take on the value of F and then of G. So for each neighbor W adjacent to the vertex, if W has not been visited, DFSW. So you kind of start recursing immediately. Okay, so that's that. Now the breadth first is a queuing idea, and we mentioned that queue idea before. So it's very, very similar. We visit vertex V. We immediately visit the vertex that's given us. So both algorithms begin at least that way. Then we put V into the queue. We visit it, we put the V into the queue. While the queue is not empty, we'll remove it into the queue, and then we're going to try to visit each neighbor W. If W has not been visited, visit this neighbor and put it into the queue. So if A has neighbors B and C, we're going to take out A, and the W of B and C will be enqueued. And so by the time we come up here to check if the queue is not empty, B and C are there. We'll take out B and go to B's neighbors. We'll take out C, go to C's neighbors. So we will then increase our distance from the starting vertex by 1 at most. And many times it's going to stay the same. Because if A has neighbors of B and C, and B has neighbors of X, Y, and Z, by the time we visit X, Y, and Z, the distance from the beginning is going to be 2, 2, 2. 0, 1, 3 children, 2, 2, 2. So the nodes that are being visited are monotonically increasing. Monotonically, no. They're not monotonically increasing. They're increasing. Better yet, they're non-decreasing. That means they cannot get less, but they can stay the same or increase. So non-decreasing means staying the same or increasing. Those are two choices. So I'm not going to bother going through all of it. Okay, another interesting part of matrices, and specifically as they represent graphs, is something called transitive closure. And I'll show you exactly how that works. So what we have is, let's suppose I have a graph with how many nodes? 8. Okay. So you can see, now let me ask you a question. Is this a directed or undirected graph? Is it a digraph or not a digraph? It is a digraph. How can you prove it's a digraph? Showing that there's no symmetry. For example, can 8 go to 2? Can 2 go to 8? Okay, so there's an edge from 8 to 2, but not from 2. So it is a diagonal. Because you can't, otherwise it would be symmetric. So it is not a symmetric graph. What do these 1s mean? 1s means that if you're at 1, you can go to 1. We need this for this particular procedure. So what we're going to do is we're going to take this graph. And you're not even looking at the graph, but I'm just telling you, this is the graph. And what we're going to do is we're going to raise this graph to a power. And the power we're going to raise it to is going to be done not arithmetically, but Boolean. So we're going to raise it to Boolean powers. A Boolean matrix, a matrix only has 0s and 1. So when I raise m to the second Boolean power, it will be another 0, 1 matrix. So here's what's going to happen. So if n, this is now simplified. This is the same graph, by the way. Remember? 8, 2, 2, 8. So now what we're going to have is we're going to take m times m to produce m squared. Here's how we're going to do it. So, you guys remember how to multiply matrices? It's fun. So, basically, in order to compute m2, just this element occurs in row 1, column 1. So what I'm going to do is in order to compute m squared, row 1, just this one element, I need to multiply every element in row 1 of m by every element of column 1 in m. So I'm multiplying essentially this row by this column. So if you take this row, 1, 1, 0, 1, 0, 0, 0, 0, take it out and now turn it on its side. And you're going to multiply with the first column. Notice that you're going to get some stuff lining up. What's going to line up? This is going to line up with itself. This is going to line up with 0. This is going to be 0. This is going to be 0, 0, 0, 0, 0. Because they're all zeros. So therefore, how do we compute this element? This element is computed by taking by the end of every corresponding. So every one of these, with every one of these, make a logical AND. So we're going to have 1 with 1. 1 and 1, 1. 1 and 0, 0. 0 and 0, 0. 1 and 0, 0. 0 and 0, 0 and 0, 0 and 0, 0 and 0. So what we have is we have 1, 0, 0, 0, 0, 0, 0. And what we're going to do is we're going to take the OR of that. So 1 or 0 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 is 1. So that's why it's a 1. Now notice that if we do this, now when we want to calculate this element here, this element is the first row, second column. In order to calculate just this row, you need to take the first row, tick, 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 and do a Boolean multiplication with the second column. So first row, second column. So therefore this is going to go with this, and that's going to give me a 1. So just that alone will make this a 1. Because once you have a 1 and 1, it's an OR. So once you have a 1, that 1 stays. Now, notice that the next element, we have a 0, 1, but this element has a 1. And this 1 is highlighted in yellow, which means it's special. So notice that this 1 corresponds to row 1, column 5. Notice that 1, column 5 was a 0 in the original matrix, but it's turned to a 1 in the new matrix. Why? Because this 1 is computed by multiplying Boolean multiplication of first row, fifth column. First row, fifth column. So therefore, we're going to go here to here, 1 and 0, 1 and 1. Notice that's going to turn on a 1. So this with this is going to give me a 1. Let's see what these two 1s mean. Why do they turn this 1 on, which wasn't on before? That's because what we have is this tells me that 1 can go to 2. Right? 1 can go to 2. That's what this one tells me. But when I multiply this one with here, this tells me that 2 can go to 5. Since 1 can go to 2 and 2 can go to 5, notice that when I do first row by fifth column, 1 and 1, this 1 and this 1 means I do 1 to 2, 2 to 5, that means 1 to 5. So this yellow shows me that I can traverse from vertex 1 to vertex 5 in 2 steps. All of the yellows are new connections. They're not new edges, they simply say you can get from I to J in 2 steps. Or, if you want to be more general, you can say you can get from I to J. You can get from I to J. Okay? So now what I'm going to do is I'm going to take M2 and multiply it again by M1, producing the third Boolean power. Let's look ahead at the third Boolean power. Notice in the third Boolean power we turn on position 1, 3. Let's see why. 1, 3. Notice that 1, 3 was off. It's still off here. Why is it on? To do that, you have to multiply the first row of M2 by the third row of M. M squared times M produces N cubed. So let's multiply the first row of M squared, which is here, by the third row of M, which is here. Notice the sequence reads here, 1, 1, 0, 1, 1, 0, 1, 0. Let's see what we're multiplying it by. 1, 1, 0, 1, 1, ding, 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 ding. This hits right here. This is a hit. So this hits on the 5th position. This is the 5th position. Okay? So what happens here is this turns on this bit. And so this is the third Boolean power. Okay, so notice that all the other yellows are also, so all of these are, so for example, the reason that we have a 1 here, which is position 4, 3, is because I can go from vertex 4 to vertex 3 in how many steps? 2 steps. 3 steps. Okay, when I say 2 out of 3. 3 steps. Makes sense, right? Now what I'm going to do is I'm going to multiply M3 by M again. Notice when I do that, do you see any yellow here? No. Okay, what does it mean? It means that no new connections were made. Well, if no new connections were made, that means that M3 equals to M4. That means that M4 times M is going to be M5, which is going to be equal to M4, is going to be equal to M3. So once you have no more yellow, no more new connections, that means you've achieved what is known as transitive closure. That means that if you have a 0, for example here, which is 7 going to 6, that means what? That means you cannot go from this vertex to this vertex at all. Can't get there. So transitive closure shows you the connectivity from I to J. Notice that I changed all the yellow. I could keep different colors like yellow, orange, etc., but I didn't keep that. So therefore, when you achieve transitive closure, what does the 1 indicate in the matrix? It indicates that you can reach from vertex I to vertex J in 1 or more steps. Or if you want to be more specific, 0 or more steps. Because the vertical is really length of 0. In order to do transitive closure, you have to have the diagonal equal to 0. If you don't have the diagonal equal to 0, you're not going to achieve transitive closure. And since diagonal equal to 0 is trivial, because it just says you can go from I to I, Mi to I. Can I go from I to I? You're there. Okay. That's what it means. Okay. Now, the next concept of graphs, we're going to talk about something called a spanning tree. A spanning tree is basically a subset of a graph such that the remaining part of the graph is connected with a minimal number of edges. And spanning trees deal with, just so you make a note of that, spanning trees deal with or undirected graphs or non-directed graphs. So this deals with not digraphs, but just ordinary undirected graphs. If we have Imagine a graph with 8 vertices. How, and it's undirected, 8 vertices, so tick, 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 8 of them. You can put them in a circle, you can put them in a line, you can put them in a triangle, however you want to put them. My question to you is, how many vertices, if I have 8 vertices, how many edges do I need to connect them? What's the smallest number of edges to connect 8 vertices?
7.
The answer is 7. Well, almost all of you came up with that number, 7. Yeah, you can imagine that. You put them into a circle. You put them into a circle, you can connect 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. So once you put one edge in, you have 2. At another edge, you have 3. At another edge, by the time you put the 7th edge in, you got 8. Okay, now, what we're going to do, what we want to do is we want to consider graphs that have a weight on the edges. And what we want is we want to create this spanning tree, which is the minimum set of weighted edges, such that the cost of weighted edges, the sum cost of the weighted edges is minimal. So edges can have a constant or variable cost. Minimum spanning tree is a spanning tree with the lowest sum of total edge costs. Let's take a look at this. So here, the big circles represent vertices. So we have 7 vertices. The little rectangles of numbers are edges with costs. So a spanning tree is any connected graph. Any connected graph with a minimum number of edges. And that always means n minus 1 edges for n vertices. But a minimum spanning tree, when there's a weight corresponding to the edges, means that the remaining edges have the lowest cost. There cannot be a lower cost of any other subset of n minus 1 edges that produces a lower cost. Now let me ask you a question. Do you think this edge with a cost of 8 could ever be part of a minimum spanning tree?
Yes.
It's the most expensive edge. So could we have the most expensive edge while trying to produce the cheapest connected graph? Which is what an MST is, minimum spanning tree. Do you think we would enjoy or pick early this expensive edge?
Yes.
No. We would not like to pick it because we want to have the lowest cost. So which edge looks most attractive? Which? 1 to 2 looks most attractive because the cost is 1. So let me ask another question, since you did so well on the first one. Would there ever be a reason not to pick edge 1, 2 with a cost of 1? I'm just asking a question. I like the fact that you're not answering quickly, because that means you're thinking. Okay, that means you're thinking. It's not obvious. Because, and I'll make this case right here, because basically, if you said, no, I would never pick 8, it's the most expensive edge. Yes, I would always pick 1, it's the cheapest edge. Then you would be answering this using an approach to algorithm known as what? You always go for the next step to be your best immediate reward. And there's a name for this kind of algorithm, and it's called the greedy algorithm. And a greedy algorithm is an algorithm that makes the next move based upon its best gain, immediate gain. That's kind of how kids work. Johnny, you can have 1 cookie now, or you can have 3 cookies after dinner. Well, to wait after dinner to get this reward of 3 cookies is too much to wait, so the child will always go for the immediate reward. Because you don't want to wait. So the question is, can we be greedy in this algorithm, in computing the MST, the minimum spanning tree? Before answering that question, let's take a look at some classic algorithms that do just that. And so one of the algorithms we're going to look at, there are two of them in the notes, I'm only going to go over one, but they're very similar. One is called Cruxell's algorithm. So Cruxell's algorithm, MST algorithm, is as following. Now we can talk about its complexity, but let's find out what exactly are we going to do. So the first thing we're going to do, we're going to take all the edges, and you can see the edges, there's a bunch of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges. 12 edges, 7 vertices. How many edges are going bye-bye? How many edges are we getting rid of? Gotta get rid of 6. We got 12, we gotta be down to 6 to have a minimum spanning tree. So, Cruxell's algorithm says sort the edges in increasing order. And when we do that, edge 1, 2 is going to be immediately the first one in line, then we're going to have this one in line, then we're going to have this one, then we're going to have tie, 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 4, 5, 6, 6, get the idea, right? I think I missed a 3 in there, a couple of 3s. So we're going to sort them in increasing order. Then we'll initialize each vertex as a single connected component. And then we're going to loop or iterate until the graph is connected at the cheapest edge, which will connect two connected components. The joint components become a single connected component. Boy, that's connected. That's crazy sounding, right? So here's another way of looking at it. We'll create a forest, F, which is a set of trees. So the forest is a set of trees, where each vertex in the graph is a separate tree. So we're going to go back to our picture, and then each of these 7 vertices will become a tree. Then we'll create a set S containing all the edges in the graph, which is 12. So the cardinality of S is going to be 12. Now, while S, the set of edges, is not empty, and F is not yet a spanning tree, we're going to remove an edge with minimum weight from S. Well, clearly, we're going to have a forest of 7 trees, 1, 2, 3, 4, 5, 6, 7. And the cheapest edge is going to be the edge 1, 2, with a cost of 1. We're going to remove the edge with the minimum weight from S. If that edge connects 2 different trees, then add it to the forest, combining 2 trees into a single tree. Add a branch to the tree. Otherwise, discard the edge. When would you discard the edge? If it doesn't connect 2 different trees. So after the termination of this algorithm, the forest has only one component and forms a minimum spanning tree of the graph. Let's take a look. So this is an analysis. I'll come back to that. But let's take a look at what we have. You can see that our sorted edges start with this one. And I pick in order the cheapest edges up to the most expensive edges. If there is a tie, it doesn't matter. It's arbitrary. So there's 2 3s. There's 2 3s. Either order is going to be okay. So on the right side here, these are my trees. Notice that they are all disconnected from each other. So there are 7 trees. I pick the first edge, which is edge 1, 2. And edge 1, 2 makes a connection from this tree to this tree, unifying that tree into a single tree. The next connected component is 2, 3. And 2, 3 would connect this tree to this tree, making 1, 2 with 3 a single tree. Next one is 4, 5. And 4, 5 connects these 2 trees, therefore unifying them into a single tree. After that, we have 6, 7, and 6, 7 connects these. And notice that now I have only 3 trees. Now I have 1, 4. 1, 4 would connect this tree to this tree. So therefore I take it, and it unifies 1, 2, 3 with 4, 5, created the 1, 2, 3, 4, 5 tree. Next, I have the next cheapest edge is 2, 5, but 2, 5 I can't take, because 2, 5 would be an edge from 2 to 5, and 2 and 5 are already in the same tree. Therefore, that would create a loop, a cycle, a redundancy, because basically everything in 1, 2, 3, 4, 5 is already reachable from 1, 2, 3, 4, 5. I'm trying to connect the graph with a minimum cost, so therefore I reject 2, 5. And I go to the next one. The next one is 4, 7. Notice 4, 7 will connect the first tree to this second tree, and there is my MST. 1, 2, 3, 4, 5, 6. Rejected, 6. So there's 6. And if you look at this, this is the resulting MST. You count it up. 3, 7, 10, so 17. That is guaranteed to be the minimum cost. What does it mean? It means that there may be other spanning trees, but no spanning tree can have a lesser cost. You could have spanning trees that have the same cost. They would also be minimum spanning trees, so minimum spanning trees are not guaranteed to be unique. They may be unique. When do you think they would definitely be unique? They're not guaranteed to be unique, but under what circumstances will they be unique? It's a good question. It's an easy question. If we have multiple edges of the same weight, it's possible we end up with a different shaped MST, minimum spanning tree. It's still going to be MST, but it will look slightly different, but it will have the same cost. Okay? Good answer. If they have all unique costs, then we cannot have any duplicate. Now let's think about an application that we'd like to make an application here. Okay? How can this algorithm, the MST algorithm, be applied in solving a problem? Let's come up with a problem. How about if I come up with a problem? Probably save some time. Okay, so what I'm going to do is I'm going to go back to the original graph with all the edges. So you understand, whatever is left here was part of the original graph. So if we go back here, notice that everything is here as the result. Except there's some extras, right? There's 6 edges that we threw away. Now, can you think of a problem that we might start out like this, and then we get to, and then we want to whittle it down to this MST solution?
Traveling
Hmm?
salesman. Traveling salesman.
Well, I wouldn't say that's an excellent guess. Not a perfect answer. Good answer, but not a perfect answer. Because traveling salesman basically need a connectivity anywhere to anywhere. It's a different problem. It's a problem we might talk about in the future also a little bit. But I'll give you an idea. Suppose that these 7 vertices represent central points within a city. So we have a city, and those 7 points are the high traffic points in the city. They're not all equally high in intensity, but they're the highest. So we found we had a city, and the city was, maybe the city was the whole page, and we basically found these 7 points. So there are still people living here, but there's few of them, and there's more here, and more, so you get the idea. Now, let's suppose that each time we make a connection from point to point, that's going to represent, for example, building a track for a subway that's going to connect those 2 hubs in the city. So to connect 2 to 3 is a cost of 2. But to connect 3 to 6 is a cost of 6. Why? I don't know. More rocks. Tougher terrain. There are variable costs, right? More hills. So, in a sense, these are the possible tracks that we can use to build the subway. We don't want to use them all. Why? Well, each of them represents millions of dollars. So this is $6 million, $2 million. Now, unless you're paying for it, the city is going to be trying to constrain its costs. So we want to minimize the cost, but we want to make sure what? they're all connected. We want to make sure people who start in 3 can definitely end up at 8. And they can, well, not 8, there's no 8, I meant like 7, oh, I got 8, was it 8? Whatever, okay. So notice that they can, but they have to go like this. They probably would prefer if there was a direct connection here, maybe. So what does this do? This is basically doing what? What is this MST doing for that problem? Minimizing the cost of building a fully connected subway system. Notice the subway can go from here to here and here to here. So it's a non-directed graph. Are you with me? Okay. So there's another algorithm for that. It's called Prim's algorithm. Prim's algorithm is very similar. You can look at it. And basically, in Prim's algorithm, I'm not going to go bothering through it. Notice that this is 7, 10, 17. Notice that we have the same cost, but actually it's a slightly different shape. We had a choice, and we made this choice, and it still is working. By the way, if you go back to my original question, if you consider only Kroxel's algorithm, my question is going to stand one more time. I want to go back to my question I threw out at the beginning, which I thought was a very interesting question, and I love the fact that you didn't give me an answer right away, because it wasn't obvious. But now, if Kroxel's algorithm in fact can be proven to be optimal, would there ever be an MST where the cheapest edge was not taken? Follow the algorithm. Prove it.
With the first tree that is connected.
Be more clear. I think
It
you're
is the
right.
first edge that we have to connect.
So the cheapest, we take the cheapest edge, and are we going to use it every time?
The very first time.
Yeah, are we going to use the cheapest edge on as the very first one? Is the cheapest edge always going to be part of the MST?
Yes.
Because remember when we start off with a forest of trees. Forest.
Your trees start off disjointed, so you have.
All the trees are immediately disconnected. So is there under any circumstances, would you ever reject the cheapest edge? No, because the cheapest edge will never create a cycle, because nothing is connected. So therefore, we can say, in Kroxel's algorithm, we will always, always take the cheapest edge. Yes? Okay, so now my next question. According to Kroxel's algorithm, when would we take the second cheapest edge?